So this is a video example on an application of momentum and energy conservation called a ballistic pendulum. A ballistic pendulum consists of a block of wood or clay or some other soft material that is suspended on a string, and then a bullet can be fired into the block, and the momentum of the bullet carries the block and the bullet both upwards after that impact. You can use this to determine the initial speed of the bullet by measuring the height of the swing. Those two are proportional, as long as you know both the mass of the bullet and the mass of the block, which are easily measured quantities. This is a fairly simple system that's used to find velocities of bullets, and it was a way that was found in the 18th and 19th centuries before more sophisticated modern technologies were developed. So let's jump into an example problem here. So we've used our ballistic pendulum, and we have measured that the height that this block rises is 0.1 meters. How are we going to calculate this initial velocity? What we need to recognize is that there are two phases of the motion. There is a collision phase and a swing phase. Let's first consider the collision of the bullet with the block. During that collision of the bullet with the bullet becomes embedded in the block. In that process, it releases heat, sound, other types of energy are released, and so we end up with not being able to use energy to calculate our speeds and velocities here because we have energy going into forms that it's difficult to measure. And so we would need to measure the velocity of the block and the bullet after the collision in some way, shape, or form, and that's not very easily done. However, we could use to our benefit conservation of momentum, and we will use that here during the collision. We're going to understand that the initial momentum is equal to the final momentum in this case because this is an isolated system. There is no other forces acting in that collision, and so momentum will be conserved. So we have our initial momentum, which is equal to just the mass of the bullet times the velocity of the bullet, and that's going to be equal to the combined mass of the block and the bullet times the velocity of the two after the impact. Now, during the swing, in the swing phase, we're going to be considering energy. At this point, the collision has already occurred, and so the kinetic energy of the block is going to be equal to the potential energy of the swing. And so we know the height, and we can calculate potential energy. That gives us the kinetic energy after the collision. That kinetic energy is a very handy number to know because you can use that to calculate the velocity of the bullet and the block after the collision, which is the only missing piece of information that we have here over on the collision side. So we're going to do that. Kinetic energy at the bottom is equal to potential energy at the top. So you have 1/2 times the combined mass, v squared, equals the combined mass times acceleration due to gravity times the height that the two swing upward. The nice thing about this, again, is that these two are the same number and your missing link. If you wanted to do one long equation and substitute in, you certainly could. For our purposes of our course, we won't do that. We'll just solve this as two separate phases. So let's actually plug our numbers in now that we have all the relevant information gathered. I'm going to start on the swing side. I'm going to put in 1/2 my combined mass, which is 8.03, times the velocity squared, and times the combined mass again, acceleration due to gravity, and the height. Find my velocity. Of course, don't forget to take the square root when you find your velocity. So the velocity of the bullet in the block after the collision is 1.4 meters per second. That represents the speed of the two right here after the collision. We can take that number and plug it in over on the other side. Once we do that, the only piece of missing information we have is the initial velocity of the bullet. So we just solve the mathematics out. We get the initial velocity of our bullet is 375 meters per second. Now you'll notice in this example, you were given height and you kind of had to work backwards to the initial velocity. What if you're given initial velocity and you'd like to solve for a height? That's the other type of problem that I could give you. That's what example 2 is about. We're still going to use the idea of the collision and the swing. In this case, since we have everything we need at the beginning for the initial momentum of the system, we're going to start there on the collision momentum side and then move to the swing side. So our initial momentum is equal to our final momentum here. We're going to solve for that velocity. This VF is the velocity of the bullet and block after the swing. And so that velocity is 3.72 meters per second. This is going to be the velocity then that we put into our kinetic energy equation. 1/2 the combined mass, 3.72 squared, and solve for height. 0.706 meters. And really, that's the meat of the ballistic pendulum type problems. They can only go one of two directions. You're either solving for height or you're solving for initial velocity. I hope you found this video interesting and that you've learned a little bit about ballistic pendulums and how they relate to momentum and energy conservation.